Here's another video of the lecture Intro PDE. In this lecture we start with chapter 3. This means we start with the Laplace equation. And we present the section 3.1, the whole section 3.1. Okay, the starting point is the Laplace equation. Laplace equation. This is a linear PDE of second order. We already introduced it, and so let's write it. We abbreviate the Laplace operator by a delta, and it's the sum over the second derivatives. Okay, so this is Laplace equation. Solutions are called harmonic functions. And it's a linear equation and inhomogeneous. Laplace equation. Now this looks minus Laplace u is equal to f. So u, the unknown function, is here some function on Rn or some domain, some real function. And f is also some real function on the domain, the inhomogeneity. Yeah? This is given and this is unknown. Yeah, typically. So we look for solutions for a given inhomogeneity f. We look for solutions of this equation. Okay, this is the main subject of chapter 3. Okay, let's start with fundamental solution. So, the starting point is that Laplace operator df du equals 0 is invariant with respect to rotations. Okay, what does this mean? What does this mean? So, let O be an n by n matrix, n by n matrix, which represents an orthogonal linear map, yeah, from Rn to Rn. Yeah, so this means it preserves the scalar product. Yeah, and so this means OX scalar product with OY is the same as, now we may calculate this. Yeah, this is by definition. If we write x and y as column vectors, yeah, then this is the same as this transposed. Yeah, okay, and then we have x transposed O transposed O y. And this should be equal to x transposed y for all column vectors x, y, in Rn. So this means that O transposed O is the identity matrix. Okay, and now let's see that the Laplace equation also transforms in this way. Okay, let's look for the function. So we make an orthogonal transformation. Y is equal to O times X. O is now this matrix. Also, if we write this out in components, this means J is equal to sum over I, sum I equal 1 to n, O J I X I. Okay, so now we want now we want to look for the function df f of Ox, and let's calculate the Laplace operator. So this is the sum over I d square dxi square of f, yeah, I don't need a bracket here, so of f of Ox. Okay, let's call the derivative with respect to the coordinates y by y. Yeah? Now, df of Ox divided by dyj. Now, what is this? Sorry. dxi. Now let's do this calculation. This is df. Now we call y equal to Ox. So this is equal sum over j. J equals 1 to n, yeah, by the chain rule. dyj of Ox times, and now inner derivative, yeah, dyj by dxi. Okay, here we have this formula. So we know, yeah, since this map is linear, so this is just equal to sum over j equals 1 to n df by dji of Ox, and then we have this matrix Oji. Yeah, here, since okay, so we have this expression here. Okay, now let's calculate second derivative. Yeah, d square f of Ox d square xi. So we should take here a second derivative. So this is sum over j equals 1 to n df by dyj of Ox Oji. And now we should calculate d by dxi. Okay, the only place is here. So we get another sum. Sum k equal 1 to n. Sum j equal 1 to n. Okay, and what we get here, yeah, well, this this is the same what we had before. So what do we have now? We get d square f by djk dyk dyj of ox and now times also maybe I write it in a new line and to make it because we do not have enough space here, so we write it in a new line. So this is sum k equals 1 to n, sum j equals 1 to n. Here we get d square f dyj and now dyk, and then we have oj I, and here now we have to take the second derivative, so we have o k I. Yeah, okay, and this matrix, what is here? This matrix moment, sorry. Okay, now we should calculate this is the result. And now what result do we get for the Laplace operator? Now let's do the calculation for the Laplace operator. So we have this, and this means for the Laplace operator, so the sum I equals 1 to n d square f of dxi square of ox, this is equal. Now we have these three sums. Sum I equals 1 to n, sum k equals 1 to n, sum j equals 1 to n. d square f dyk dyj oji oki. And now of course we can reverse the order of the sum. Okay, since O transpose O is the unity matrix, so we have that the sum I equals 1 to n, here this is exactly, here we get exactly this expression. This is oji oki. This is here transposed. If we transpose it, we reverse it, so we get exactly this product. So we see this is delta jk. This is delta jk. Okay, so what do we get? So this means sum d equals 1 to n d square f over dxi square of ox. Now we can take the sum over the j's, and by this expression, as we calculated this sum, so this is sum k equals 1 to n, sum j equals 1 to n, d square f dyk dyj delta jk. Now we can calculate the sum j, and get only an expression if j is equal to k. So we get k equals 1 to n d square f djk square. So here's an ox of ox, And so we indeed get, this is again the Laplace operator evaluated at OX. Yeah, so this shows that this is really invariant. Okay, I really did this very explicit by using matrices and indices. One could also write this more elegantly by using this equation. Yeah, and yeah, also you can think about it. But this calculation shows that Laplace equation is invariant. Yeah, Laplace equation is invariant with respect to orthogonal transformations. Particular all rotations. And of course, since the coefficients here are constant, it is also invariant with respect to translations. Yeah, so it has the full Galilei group as an invariance group. Okay, now this observation, for this reason, yeah, so we look for solutions of which are also invariant with respect to rotations, to all rotations. And this means, yeah, that f, a function which is invariant, yeah, this means u of x has the form that it's just a function of v of r, and r is just the absolute, the length of the vector x. So v of length of r, yeah. So here r is equal, and this is the square root of, by Pythagoras, it's the square root of the length square. Now let's calculate the Laplace operator. Yeah, what is Laplace of u under this assumption? So let's first calculate the gradient of u of x. If it's of this form, yeah, then by the chain rule, this is v prime of r times, and the inner derivative, of course, we should take the gradient of dr. And what is the gradient of r? Now r is square root of x times x. Yeah, so x times x 1/2. Now, what is the gradient? First, what is the gradient of x times x? Yeah, and I claim this is d by d. No, let us use this abbreviation which we already introduced. Di of x scalar product, also d1, d2, x times x, and so on. And dn of x times x. And x times x is, of course, the sum over the squares. So here we get 2 times x1, 2 times x2, and 2 times xn. So this is just 2 times x. Okay, this is the inner function. Yeah, I do it now very explicitly. Yeah? And what is the outer function? This is the square root. So gradient r is now, inner function is this term, so we get 2 times x, and outer functions is square root 2 times square root of x times x. So this is x over r. Okay, so we have the first result. Gradient u of x, if it's of this form, is just v prime of r times x over r. Now now we take the Laplace u of x, and this is divergence of gradient of u of x. So this is divergence of v prime of r times x over r. Okay, then here, first we calculate here, we have to take the derivative here and then here. So if we take here the derivative, then we get a double prime of r, and then again x over r times x over r. Yeah? We do just apply just the same formula and take the scalar product with x over r. So we have this expression. Now here, what is gradient divergence of x? Divergence of x, no, this is d1 x1 plus and so on dn xn, so it's just n, yeah, because this is 1, all is 1. So it's n. So we get here plus v prime of r times n over r. And now finally we have to take here the derivative. This is again a function of r. So, but it's minus 1. So the derivative is v prime of r x. Now 1 over r is 1x over r squared times x, and we again have to multiply it here by x over r. Yeah, since with respect to r, immer when we take the derivative with respect to r, we have to multiply it here by the inner derivative. So so we get this all together. So we get, okay, so now collect all terms. X squared is of course the same as r squared. So we get v double prime. X squared is the same as r squared. So this cancels. Then we get plus v prime of r, and then we have n over r, and this here is minus x squared over r squared. This is 1 over r. Yeah, so we get here I missed. So we get v double prime of r, and this here 1. Yeah, this in the bottom. This is an r. Sorry. This is an r. So plus n minus 1 over r v prime of r. Now this is our result. Yeah. So Laplace equation means v double prime of r plus n minus 1 over r v prime of r is 0. Okay, and now let's assume that a function doesn't vanish, or at least now we do a calculation where this function doesn't vanish, and then we can divide here, yeah, and then we obtain v prime of r is equal to minus, so 1 minus n over r. Yeah, so this is our first, in this form we can bring the Laplace equation. Yeah, and now this is a nice formula, yeah, because this is the derivative. On the top we have the derivative of the bottom. Yeah? On the top, the derivative of the bottom. And then you know the whole thing is the derivative of the logarithm of the bottom. Yeah? So v double prime of r, v prime of r is d by dr of ln v prime of r. Yeah, if we calculate here, then we get this. Yeah, and this is the derivative. So we now integrate once. Yeah, then we get of 1 minus n ln r plus some constant. Yeah, okay, this constant here we don't need. So we integrate once. Yeah, very nice. Now we can integrate once and we get ln v prime of r is equal, we can even put here an absolute value, yeah, as long as it doesn't vanish. This is equal to 1 minus n times ln of r plus some constant, first integration constant. Yeah, so we integrated this one. Okay, maybe also we just look for a solution, and okay, so we integrated this once and obtained this equation. Now we can of course exponentiate, yeah? Yeah, and then we get y prime of r is equal to exponent here. Now, this exponent is r to the power of 1 minus n, and times some constant, c prime. Yeah, an exponential of a constant gives a multiplicative factor. So this, now we have this equation. And now we can integrate a second time. Now we integrate another time. Yeah? So let's integrate this, and what we get is v of r. Now if we integrate this, what do we get? Now for n equals 2 we have to be careful, because then it's just g prime of ln r plus c double prime, another integration constant. If n is larger than 2, then this exponent is here not minus 1, so then we get c prime r times, and then we have to increase the exponent to integrate 2 minus n over 2 minus n plus c double prime. Okay, so here we have written this in this form. Yeah, this means just this constant here is a different constant than this constant here. Yeah, okay. So, but these are clearly the same. Yeah, just this constant here is another than this constant. Yeah, it differs by this factor. So very nice. So we have now calculated all functions, harmonic functions, which only depend, which are invariant with respect to rotations. Yeah, we get this solution. Okay, and now we introduce the so-called fundamental solution. And the fundamental solution is just a special choice of the constants. Yeah, we just make a special choice. We choose this constant to vanish, to be 0, And here we make this constant. And omega n is the volume of the ball B01, also the unique ball with unique radius, yeah, in Rn. Yeah, omega n, this is just a positive constant. Yeah, omega 2, what is omega 2? No, it's of course pi, and so on. Okay, and then we make this special choice. Yeah? We will later see why we have chosen this special constants. Yeah, we will see this now in the next theory. Yeah, because due to this special choice, we have this very nice observation. Now, first, let us understand what does this mean. So we have a twice continuously differentiable function f with compact support. Yeah? The 0 here means with compact support. 0, 2 of Rn twice continuously differentiable functions with compact support in Rn. So they vanish outside a compact set. And the support is the closure of the points where this function do not vanish. Okay, and this is this set, and then the claim is then we have a solution of this function. Okay. And we write this in this form. Okay, now look at this first formula. Yeah, we have du of x is equal to f of x. Now question. If we, first of all, yeah, that this is equal to this. This we have already seen before, yeah. Since this is convolution, yeah, this is convolution of phi with f, and we already observed that we can write the convolution in this way and in this way. This is just by substitution. Yeah, here we substitute x minus y and call it z, and then by translation invariance we have the same measure. And if z is equal to x minus y, then y is equal to z. X minus z. Okay, so this is just a substitution. Now let's use the first formula, yeah, and calculate du of x. I do now a calculation. Is d of phi of x with respect to x, yeah, x minus y, f of y. Rn. Now we put this in, yeah, since this is differentiable and linear, so it should be possible to put this in. dx y phi x f of y dny Rn. Now this is harmonic. Yeah? We determined phi that this is harmonic. So this should be 0. Why is this not 0? Yeah, what is the reason that this is not 0? Okay, let's have a careful look at our function. Yeah, our function here, this has a singularity at 0. Phi has singularity at 0. Yeah, so there it does not obey, there it's not harmonic. So phi is only harmonic on the complement of 0. Yeah? At 0 it's non-harmonic because there it's not even defined. Yeah? Okay. And this is the explanation. Yeah? So this calculation is really correct. We may put this in, but this does not vanish. This does not vanish because phi has a singularity at 0. Yeah, very important. You should understand this. Okay, now let's prove this theorem. Yeah? Proof of the theorem. Okay. And we want to use that phi is harmonic here. So first we use this expression here. Yeah, so first we use this expression. And since f is twice continuously differentiable, yeah, we can put this in. Yeah? So we indeed have du of x is, now use this expression, integral Rn phi of y. Now I write, I take the Laplace operator with respect to x, f of x minus y dny, Lebesgue measure. So, now we split this. We choose a small ball of radius epsilon, and later we will take the limit epsilon goes to 0. So small ball b0 epsilon phi of y, yeah, because at 0 we have this problem. So dx f of x minus y dny plus, and here we have this integral Rn and the complement phi of y dx f of x minus y dny. Okay, and this we call I epsilon, and this we call j epsilon. And later we will take the limit that epsilon goes to 0. So let's see whether we can control this in the limit. Yeah. Can we control the first term in the limit? We shall take the limit epsilon goes to 0. Okay, so let's take the limit. And f is continuously differentiable twice. So dx f of x minus y is on the epsilon ball, 0 epsilon, bounded. Yeah. Also on the closure of this ball, it's continuous and therefore it's bounded. Yeah, because a continuous function and a compact set is bounded, and this set is compact, is bounded. So we just take the supremum norm of this function here on this set, and then estimate this function. And phi itself, it's positive. Yeah, at least also here for small. If epsilon is small, yeah, then the logarithm becomes negative on this epsilon ball, so minus the logarithm is positive. So phi is positive. So let's try to estimate this here, and then we get, yeah, this, the absolute value is smaller or equal some constant times the supremum norm of F on Rn, the supremum. Since it's compact support, we have such a supremum, times the integral over the ball, 0 epsilon, and y dny. Also hier this constant. Yeah, here, okay. Here this constant, sorry, this I can remove. Yeah, this is 1. Yeah, because we just have this. Okay, now let's calculate this function here. Yeah, and the integral, since it only depends on the radius, yeah, we can use polar coordinates. Yeah, so this here, also sorry, we can remove this constant here. Okay, and this here, yeah, this is dxf L infinity of Rn, some number. And what is this expression? Yeah, we want to understand this in the limit that epsilon goes to 0. So this is just the volume of omega n times integral from 0 to epsilon. And now we should take these functions. Yeah. So we should take this function, which only depends on the absolute value, and then times Rn minus 1 dr. Yeah, and here we should insert this function. Yeah, so for n equals 2, so this is some constant. So for n equals 2, we have to find antiderivative of ln r. Yeah, and okay, this is just antiderivative of ln r. Antiderivative ln r dr, just an antiderivative. Okay, this is r times ln r plus 1. Sorry, minus 1. Plus some constant. Now, since we evaluate the absolute value, yeah, we get this. Yeah, for this integral here, we can estimate it in this way. So you see, it goes to 0 if epsilon goes to 0. It clearly goes to 0 if epsilon goes. And in this other situation, yeah, 1 divided, also r here we have in this other situation, here the power is 1 less. So this this is correct. Yeah, this integral is r dr, so we get an r square. So if we evaluate, we get this. Yeah, so all together we have this estimate. Yeah, and this proves limit of I epsilon goes to 0 is 0. So in the limit, this gives no contribution. So this we can forget. Now comes the next term. Now we only have to take into account J epsilon. Yeah, J epsilon. Okay, so in the limit we have this, and now we come to J epsilon. And for J epsilon, now we use the divergence theorem. Yeah, the divergence theorem. Yeah, because clearly here if we take the derivative, the second derivative x of f of xy, yeah, because its second derivative is the same as if we take second derivative with respect to y. Yeah, because it's as a first derivative we get a minus, since we have here a minus. But for second derivative we have the same. So we may replace f here. We insert, instead of derivative with y, we take derivative with, instead of derivative with respect to x, we take derivative with respect to y. And now we make an integration by parts. Yeah? Then we get this boundary term and this other term by integration by parts. Yeah? By integration we have this boundary term and this term. So again we have now two contributions. And now we want to estimate this term. Yeah, so now we want to estimate this term. Now this is a boundary integral. Okay, on the boundary, yeah, clearly this function here, we evaluate, also the function phi is constant, so we should take the length of the volume of the boundary times this function. Okay, and what is the volume of the boundary? So dB0 epsilon, and from this, sorry, the volume of the boundary, so yeah, this is clearly some constant times epsilon to the power of n minus 1. Yeah, for 2 dimension, yeah, because it has dimension n minus 1, and if we rescale everything by epsilon, then all dimensions are rescaled by epsilon. Since it's n minus 1 dimensional, yeah, we have this. Okay, so we get here for n equals 2, we have an epsilon, and itself the function is bounded by the logarithm, so we get this estimate. And for n larger or equal to epsilon, we have here again a 1 higher power than the phi, so we have 1 epsilon. So this again implies that limit epsilon goes to 0 of L epsilon is 0. Yeah? So this does not contribute. So the only thing which we now have to take into account is K epsilon. Now, what is K epsilon? Sorry. K epsilon was defined as this term here. This term. Okay, now we do a second integration by parts. Yeah, so we also want to move this to here, yeah, to use that this is harmonic outside of 0. So we do a second integration by parts, then we get this term, yeah, since minus minus we get plus, and we get this boundary term. Yeah? So we get this boundary term and we get this term. Now, away from 0, yeah, on Rn without 0, we have that phi is harmonic. Yeah, so this vanishes here. So this is very good. This term vanishes. So it only remains this term here. So this term. So this is now our result. Yeah, this is now our result. And so this means now we have to calculate this expression. So first, let's calculate the derivative, the gradient of our function. Yeah, let's calculate the gradient. Yeah, okay. And let's recall gradient of a function of u. sorry, let's recall this formula. U of x for u of x equal v of r, a function which only depends on radius. This is v prime of r times x over r. This we calculate. Now we use this formula. Now we use this formula. Okay, then we get y over r, and the derivative. Since recall, this is our definition. Here we get this factor times 1 over, this factor is important, but here we get 1 over r, and here we get n minus 2, this cancels with this n minus 2, n minus 2 times x to the power of n minus 1. Since it's in the, we have to decrease the exponent by 1, but the exponent is minus 2 minus n. So we get 2 minus n, so cancels with this, so we get a minus, so it's minus 1 over n omega n x to the power of n minus 1. So this is the gradient here. This is here minus, and now since we have to multiply it here, we get one higher order, and we have still the y. So this is the result. This is the result of this function. This just follows from this formula. Okay, the outer normal is clearly, it points outwards. So here we have a vector y. It's just a normal vector. It's y over y. Y square. But the outer normal of the domain, our domain sits outside. This points inwards. So it's minus y over y things. Since our domain sits out, so we have this. Okay. Maybe you ask yourself, maybe apply the divergence theorem, because for the divergence theorem we needed that the domain is bounded and the outside is not bounded. But remember, f, the function f, has compact support in our statement. So there exists a large ball. There exists a large ball with support of f inside this ball. And then we have here this unit ball, and then our domain looks like this. And then it's still bounded, and everything is obeyed, also the condition is fulfilled, and divergence theorem applies. Divergence theorem applies. Okay, so we have this, and of course at this boundary f vanishes and all derivatives vanishes. So we get no contribution here. We only get a contribution. Okay, so we have we are finally at this point here. Now the volume, also here we calculate the volume of, let's call it sigma n, the area of the unit sphere. Now by polar coordinates, if we just calculate the volume of the unit ball, by polar coordinates, it's sigma n times r to the power of n minus 1 dr. And if we integrate this from 0 to, we get this. So sigma n, the volume, is just n times omega n. the volume of the boundary, sigma n, or the area, maybe I should say the area of the hypersurface, which is the boundary. This is n times omega n. Yeah, this is here bipolar coordinates. Okay, so we know that n mal omega n is nothing else but the area of the boundary. So this whole expression here, yeah, is if we multiply this by the outer normal, yeah, then if we multiply this by the outer normal, then we get plus y squared divided by y to the power of n minus 1. Y squared is of course, so we get just the area. So this is just what we see. We really get the mean value, the integral of the function f on the boundary of the epsilon ball. Yeah, so what comes out, k epsilon is the mean of f on 0 epsilon. What means mean? This is the integral. So this is integral over f d sigma of the ball, 1 divided by area of the, yeah, so we already understood this is sigma n. So I write sigma n. So this is the result. This is what we get. We should be careful. We calculated the Laplacian. Yeah. So we calculated the Laplacian. Yeah, and so we get a minus. Yeah, this is the and now we should take the limit. Yeah, okay. So let's write down our formula, what we finally have. So all together we have Laplace u of x is equal minus, limit, we should take the limit. So it's limit epsilon goes to 0 minus, and then integral over the ball 0 epsilon f d sigma 1 over sigma n. This is our result. And now we may calculate this limit. Yeah? By continuity, yeah, the values of f are nearby to f at x epsilon. Yeah, in general here. Yeah, so f so I should write x minus y d sigma y. Yeah, so this and this limit here by continuity is clearly f of x. Yeah, since if we make epsilon small enough, the values on the bound on the whole ball minus f of x is arbitrarily small. Yeah, and so and the mean value then of course gives just f of x. Yeah, okay. So this is f of x, and for this reason we have proven this with a minus. Yeah, so we have proven this, and this was exactly what we wanted to show. Yeah, so in particular minus Laplace u is equal to f. Okay, now finally, just a final observation. We may write this also, yeah, this is equivalent to the statement that minus Laplace phi is the same as delta distributions, as distributions. We already noticed that phi at 0 has a singularity. And here we see that this singularity has such a behavior that as a distribution, the second derivative is really the delta distribution. Yeah, and one can improve this whole estimate, and then one gets, one can show that in a weaker sense, this is also true for larger classes of functions. Yeah? For L1 functions, as a distribution, this solves. Yeah? This follows also from this. Yeah? That now, since this solves as a distribution, this equation, then as a distribution for FL1 functions, we really obtain as a distribution also an equation, a solution of the Laplace equation, the Poisson equation. Okay, now this is the end of section 3.1. Let's recall what we have done. We first introduced Laplace equation, then we introduced fundamental solution, so we calculated all solutions which are invariant with respect to all rotations or all orthogonal transformations. And then we found out that with some special choice of the constants, we then get a solution of the inhomogeneous equation. Yeah? This is some surprise, yeah? Because phi is first calculated as a harmonic function, but we get a solution of the inhomogeneous equation. Okay, and then we calculate this. Yeah, we made some. We had to be very careful in the calculation. Yeah, but we have been very careful. Yeah, because phi has a singularity, but the singularity is not so bad as a distribution. It's well defined, and we calculated. As a distribution, this derivative, and showed that this is in fact solution of Poisson equation. So, thank you.